On tonight's show, Kevin dates a turbine. I wear a ridiculous blazer. Kevin falls asleep. This is Tip Gear. And we begin with the news. So, the Extinction Rebellion protests have been happening in London this week.
Yes, indeed. Melting glaciers, extreme weather, rising sea levels. Global warming poses a real threat to the future of our society.
Quite right. We need an innovative solution to deliver clean energy across the globe.
So, as our government's been a little bit busy with our friends in Belgium, we decided to take this vast burden on ourselves and solve the issue.
So we've decided to build a small wind turbine that can be put into households across the globe and harness the power of Mother Nature herself to put an end to this protesting.
Well, and climate change.
Ah yes, and climate change.
I mean, how hard can it be? So, the plan is to make a clockwise spinning, horizontal axis wind turbine from ABS plastic. It's got to have a weight of less than 200 grams and fit into a rapid prototyping box of 400 by 150 by 100 mil. It's going to have a max RPM, so it's revolutions per minute, of less than 3,000, which is significantly higher than real-life wind turbines, and it's going to be optimally tested at 6, 8, 10 and 12 metres per second to give a tip speed ratio of between 3 and 8. Tip speed ratio being defined as Q graphic, the angular velocity times the radius over the free stream velocity.
But what are we going to do to make our turbine revolutionary? I mean, we need a really good idea to make ours the best.
Yeah, how about a box wing design?
What's a box wing?
A box wing would look like this, and it has the benefit of increased structural stiffness and reduced induced drag.
What do you think, Tom?
I see.
How do you even design a turbine?
Initially, we started our analysis of the chord length and twist distributions by considering a simpler two-bladed design. The advantage of a two-bladed design is it's easier to manufacture and has a reduced weight compared to a three-bladed design. In addition, we chose a TSR of 5. This has a nice compromise between aerodynamic and structural considerations.
So, at the likely Reynolds numbers we're going to encounter, which are of order 10 to the power 4 and 5, it was determined that the optimal lift to drag was obtained by the SG series of airfoils. In particular, the 6043, which was tested at 7 degrees incidence, and the 6040, which was tested at 9. These are specifically designed for use on small wind turbines.
So next, this is how we calculate the optimal cordless distribution. We first discretize our blade to a number of elements, and at each element, we calculate the optimum induction factor that generates the highest power output using this cubic equation. And then we insert that induction factor into this big formula with a number of pages of mathematics. You will come up with the cordless distribution we have. For our wind turbine, due to manufacturing constraints, we've chosen our blade radius to 0.37 meter. Considering about the structure stiffness, we've chosen a thicker airfoil near the root and a thinner airfoil near the tip. To calculate the actual twist of the airfoil, we first discretize the blade into 80 segments. For each segment, we calculate the axial induction factor and tangential induction factor accordingly, which will give us the flow angle by trigonometry. After all, the pitch angle of the airfoil relative to the rotor plane can be calculated from the flow angle and the angle of attack of each airfoil section, chosen to maximize the lift and drag ratio.
So, after we calculated the chord and twist distributions for our simpler two-bladed design, we then moved to figuring out how we transfer this to our box wing design. We did this by splitting the chord up into sections of 1/3 and 2/3, with a separation distance such that the wake from the top blade would not interact hugely with the bottom blade. This separation of the chord lengths resulted in a 44% mass reduction and an increase in the second moment of area by 100%, adding structural integrity to our design.
So Kevin, what do we have here?
What we have here is the aerodynamics of splitting one blade to a two blade.
Okay, so what kind of effect does it have?
Well, you remember our optimum cordless distribution calculation. We figured out that the optimum cordless is inversely proportional to the number of blades, which means that the sum of all the blades, of the chord of all the blade is always a constant.
Interesting. What about F, Prandtl tip loss factor?
Well, Prandtl tip loss factor takes account for the induction generated by the helical vortex generated by the turbine blades, and it is calculated using this formula. From MATLAB, we calculate the Prandtl tip loss for both 2-blade and 4-blade, and we consider them to be very close to each other until somewhere near the tip.
Great stuff.
I slept over structure. What have we got here?
Well, basically, we've modelled our turbine as two beams connected to a fixed end over here. We calculated all the aerodynamic loads and the centrifugal forces acting in the beam, but we neglected the weight because it's very small in comparison to those loads.
Then why does the top blade end here?
Basically, if we extended this any further, the chord distribution would not allow us to maintain those loads in the structure because the chord would be too small.
It was designed in Creo-Parametric 3.0. So here we have the completed turbine, which consisted of two parts, a left half and a right half. As you can see, the part is constructed of a nose cone and two blades. The cone itself is ellipsoidal in profile, had mounting holes for the hub in the centre, as well as some glue point. The top blade and bottom blade were actually mounted on different darting planes within the model to allow for some variation in the design process. That's in terms of moving them more forwards and backwards of the nose cone. Here are the varying cross-sectional aspects across the blade, growing at the root, then diminishing at the tip, with a slight kink just after the join.
After building the CAD model, CFD simulation was performed using ANSYS to find the optimum TSR. At wind speed 12 meters per second and TSR 7.5, our turbine generates the highest power coefficient of 0.48, 80% of best limit. However, the CFD simulation considered the structure to be rigid. It would be beneficial to analyze the aeroelastic effect. Unfortunately, finite element analysis was limited by student license.
Now it's time to build the best turbine in the world. As for an expert opinion, Dr. Ananya Dubey is the head of the Propulsive Aerodynamics Ultrasonic Laboratory, or PUL for short, at Imperial College London.
So, here are our designs.
Oh wow, that's quite an interesting looking turbine.
So how do we build it?
The hub will be manufactured from an aluminum block by CNC machining, which is a high-precision, computer-controlled subtractive manufacturing process. First, the block was reduced to a small cylinder with a mounting hole, and then the hexagonal shape was obtained using a 4-axis machine.
The turbine was printed, sanded and tested in the T2 wind tunnel. Well, that went well, and evaluating the power curves, it seems like we've got a clear increase in progression in power from 6 until 12 metres per second, maxing out at 98 watts at around about 2000 RPM.
Unfortunately though, at 2000 RPM, it appears that we excited the structure at its resonant frequency, causing large vibrations and fluctuations in the power plot.
Also, looking at the CP over TSR graph, reminding the fact that we actually designed our TSR to be 5. And TSR 5 is actually show some stalling there, and compared to the CFD result of a optimum TSR of 7.5, the actual experiment TSR is actually only 6.5. So what's that happening?
Well, if you look at the structure, it's fairly flexible, but ultimately we've got a decrease in power as we move away from LOVD max.
So, do you think our boxing design actually worked?
Yes. What you're looking at is the future. Sleek, elegant, efficient, and with a high power.
So we thought we'd actually done something right.
Well, although this turbine is very good, the performance is not as good as the CFD prediction. This could be due to the printing errors of the turbine and the structural deflection of it.
And on that bombshell, it's time to end the show. Good night.